Okay, let's see where we are on the product and the quotient rules. Let's look at the verbal statement of the product rule that we got first. It was that the relative change of a product is the sum, the relative rate of change of a product is the sum of the individual relative rates of change. We had to go to the idea of a relative rate of change to get such a simple statement, but I really think it's such a beautiful form of the product rule, it was worth it. Okay, and remember that this was only approximate for like a delta U and delta V, and the delta, the overall actual change in like a delta UV. That's like when we let the workman work for 10 days or some significant period of time. We saw that this was an approximately true rule, okay? But it becomes exact in the limit. I'm not using my, I can't draw the picture real easily, but what we saw was that the extra tiny little rectangle that was screwing up this law became less and less and less significant as we make like delta t very, very small. So as the limit delta t goes to 0, which is exactly how we take the derivative to find things like du, dt, things like that, the instantaneous rates of change, then this rule became actually an exact rule. Okay, and so that's great. So that's a nice statement of the product rule, but how does that help us in with terms of algebra? Well, we need to turn that into a rule about like primes and things like that. Okay, so we have two functions. Okay, we have two functions, f of x and g of x, and we got a little bit of practice doing this experimentally, but now we just want to codify it. Two functions, f of x and g of x. I don't know why I displayed those. And we want to know the rate of change, the derivative of the product of those guys. It's very, very, very important what order we're doing this in. We take the product, like we take the product of length times width to get area, and then we investigate the rate of change of that. This is absolutely not equal to f prime g prime. That's not at all what we discovered. Okay, it's not equal to that, and you've got to be very careful about that. But what we did discover was that there's something very simple. If we look at the rate of change of fg, the product of those two guys, and then we relativize it, we say, let's actually take that and divide by the quantity fg itself. So like if f and g were length and width, this is the area, and that's the rate of change of area, divided by the area. It's the relative rate of change. What we got was, okay, we just have to write this out. So that's the relative rate of a product. Now, what's the relative rate of change of the first guy? It's the rate of change, f prime, over f. Plus, there's the sum, g prime over g. Okay, that's the product rule. That's the product rule in a beautiful, beautiful form. Relative rate of change of a product, with the thing in the denominator here making it relative, is the sum of the relative rates of change of the individual quantities. Okay, so that's not how you usually see the product rule, but guess what? It's not that hard. We just multiply by fg. Okay, so we take what's on the right here, and we just multiply that by fg, and that by fg, and a nice thing happens. We get f prime, the f's cancel, and we get g, and here we get f g prime, because here the g's cancel. And I switched the order because I like to write it in this way for various reasons of my own. F prime g plus f g prime. Derivative of the first times the second plus the first times the derivative of the second. It's a little bit of a kind of a complicated rule. Let's just put f g prime here again. Okay, but that's it. That's the rule. And it's really not that complicated when you think of it as relative change. I love this form. Relative rate of change of a product is the sum of the individual relative rates of change. Okay. So, for example, we can use that to do something like the derivative. I'm going to have to use the other notation for a second here because I don't have names for these guys. Like x cubed times e to the x. Okay, let's put that into this kind of form. It's the derivative of the first, which is 3x squared, times the second left alone, plus the first left alone times the derivative of the second. Now, what's special about e to the x, of course, is that if you don't differentiate it or you do differentiate it, you get the same thing. So we actually get an e to the x coming out as a common factor, which is kind of nice. 3x squared plus x cubed. Okay. So that's a very explicit use of the product rule in this form for just a plain old derivative. Okay, what about the quotient rule? In our investigation, we were looking at slopes of lines, things like that. The main thing is just it was the quotient of two quantities. And here's what we got. Our guess was the relative rate of change of a quotient of two quantities. In that case, it was like v over u. Here I have to be careful about, and I'm going to name them because we have to be careful about the order much more carefully than in the product rule, is the relative rate of change of the numerator, here it was v, minus the relative rate of change of the denominator. And it's really important that it's numerator minus denominator. Okay. So now here, they were just two random quantities, v and u. In our case, it was like length and width, and we were taking the slope of a line or the diagonal of a rectangle. But what if we had two functions? And this is really just a change of notation, f and g again. Okay. And we want to express this in terms of the rate of change of their quotient. It's going to look a little complicated, but I saw people writing it down of their own accord. And so we're going to take f over g. That's the ratio of these two guys. And we're going to take its derivative. But we're going to realize that this rule only seemed to be simple when we actually looked at that as a ratio of f over g itself. So this is kind of weird. The ratio here, the slash, the diagonal slash, is because we're interested in a quotient, in a ratio. The horizontal bar, the reason we're taking a quotient there is because we saw that relative rates of change actually behave in a simpler way than an absolute rate of change. So there's different reasons for taking the quotient. It looks a little ugly with the compound fraction nature to it, but it really is a good idea. Okay, so we can now write that out. Okay, it's the relative change of the denominator. This is gonna. The other side looks exactly like the product rule, but with a minus sign. And then minus the relative, so that's the relative rate of change of the numerator minus the relative rate of change of the denominator. And we talked briefly about how it kind of has to be that way and not backwards to get the right kinds of numbers, plus and minus. So even though this looks complicated, it really is a beautiful rule, and it's incredibly parallel to the product rule. That's one thing that's confusing for most people about the product and quotient rule. The product rule is not that hard to remember. It's kind of a pretty formula, even though it's more complicated than what most people expect. The quotient rule seems to be just kind of weirder for most people. If you express it in terms of relative rates of change, it's not weirder at all. All you do is change product to quotient and sum to difference, just plus to minus. But let's look at what would the book's version be of this. Okay, we're going to take this and we're just going to multiply by f over g on the left and on the right. So that just goes away. Let's see, I think I have to just like cut this out, paste, repaste. Okay, now here I'm going to be multiplying by f over g. And here I'm going to be multiplying by f over g. Okay, so we get a nice thing happening in the first term. The f's cancel, but here, the g's don't cancel. Oh, wow, okay. And so, in fact, because we're getting a g squared here, and once those f's cancel, it's a g here, most people just put it over a common denominator of a g squared. So I'm actually going to promote this to be, just to get the common denominator, fg over g squared. Okay, so now it's going to be, now the f's still cancel, and I get f prime g minus fg prime. And I switch the order again because I like it that way. Now that doesn't look too different. Again, it looks like the product rule, but a plus changed to minus. But then there's this denominator of g squared. Wow, that's kind of weird. But I claim that one way to understand that is that this isn't really the real nice quotient rule. This is the one where we forced ourselves to write it as just an absolute rate of change and not a relative rate of change. So that's the price we pay. So the derivative of a quotient is this somewhat complicated formula. Okay. So for example, I don't want to make this too long, but here's an example. The derivative, now switching to the d by dx notation so we don't have to name the functions, of like x squared plus x over e to the x. Bring back our friend e to the x. Actually, no. Let me just do polynomials. Over x cubed minus 2x squared. It's going to be kind of messy, but I want to show how this works. So big quotient, derivative of the top, 2x plus 1, times the bottom left alone. That's what this part says. Derivative of the top times the bottom left alone. You do really want to memorize this formula as is, by the way. I like deriving it using relative rates of change, but you do need to memorize it as is as well. Okay, minus the top left alone. Some people have various mnemonics for this, but I think you just have to do it enough and pay attention. And then times the derivative of the bottom. That's 3x squared minus 4x. Ooh, that's getting really long. Let me take down the magnification for a second. I hope that's not too small. Over the quantity x cubed minus 2x squared squared. Wow. Now that's going to simplify. I'm not going to go ahead and simplify it right now to save time in the video, but I'll just make a note. You almost always want to simplify, expand, and recollapse the top, but you often, very, very rarely actually, do you have to do anything with this. You usually leave it as is, so don't foil that out unless you're absolutely forced to. But do expand and recollapse and recollect the top. It's the right thing to do. All right, that's good.